Okay, thank you very much. Um, so I'll be speaking about some efforts in our lab on perception and simulation in the context of self-driving. So building upon what Laura discussed at length. I think one super interesting starting point is the fact that there's some version of simulators that are actually available now for people to use. And perhaps the first instantiation of this was NuPlans. So this notion of actually taking pre-recorded data sets and turning it into a live interactive simulator that you could run a planner on and evaluate. And so this I thought was a fairly recent but very sensible way to think about it. And of course, since NuPlan, there's been other efforts from Waymo as well. So what I wanted to talk about, three specific pieces of work that we've done in the context of this. The first was our own entry into NuPlans, and then some sort of lessons learned from that space. Um, Okay, so first I wanted to sort of dig into what does it take to turn a recorded data set into a simulator. And importantly, when we say simulator here, one thing that's different than what Laura talked about is that this is not really a sensor simulator. Maybe I would call this more like a behavioral simulator. It operates at the level of objects and tracks. But nonetheless, this is still useful for, let's say, focusing a bit more on the behavioral aspect of how do things move and react with regards to one another. It seems like the sensor simulation part, there's been a lot of impressive success on looking at some of the work that Laura pointed at. Okay, so first, one of the starting points for thinking about how to take recorded data and turn it into a simulator is how do we evaluate this? And the first place I've seen this laid out was in the NuPlans challenge. So I just wanted to talk about this. There are three specific ways of, if you have a recorded log with the ego vehicle moving around in an interactive world, to think about how to evaluate a new plan for the ego vehicle. The easiest way is the ego vehicle actually went some trajectory in the future. Let's say this red path, and you can look at the plan for the ego vehicle that is given by a planner that's actually being evaluated in this simulator, and you can look at the difference between where the planner thinks the ego vehicle will be in 5 seconds from now and where it actually is. And then look at the deviation. So I might think of this as a forecasting metric, but applied to the ego vehicle. What's much more compelling is, well, you actually let the ego vehicle drift from the recorded path. So if that happens, if the ego vehicle says the plan says to go straight, then it continues going straight. But because everything else is a recorded data set, all the other agents can just play back the way that they move. So one problem with that is you'll see behaviors like this, where the ego vehicle might decide to stop, and then everyone else will just continue to move because that's what they did in the recorded data. And so we'll call this a closed loop ego simulation because the ego vehicle can change, but an open loop agent simulation. And of course, what you really want is a reactive simulator where if you do something out of the ordinary, the rest of the world reacts. And so the NuPlans define this as a closed loop agent simulator where the rest of the agents don't just play back what they did, they respond to what the ego vehicle is doing. So another way to think about this is that this simulator should behave like a game. I should be able to joystick control what the ego vehicle is doing, and stuff should react to it. Okay, and the first blush is like, okay, well then how exactly should agents react? And there's various ways to go about this, but it turns out a really simple model for reactive control is a PID controller, a proportional integral derivative controller, which you might remember from your old controls class. But in the context of vehicle dynamics, this is oftentimes called an IDM or intelligent driver model. So this always kind of perplexed me, but I just wanted to hopefully not scare you guys, and that it's actually just about 10 lines of Python code. It's extremely intuitive. There's 5 big parameters that says how close are you willing to get to the lead vehicle, what is your max acceleration, what is your min acceleration, and given all this, you can write some pretty simple logic that basically lets every agent it will let all other vehicles almost behave as if they're on adaptive cruise control. That's one mental model I have. is that you can have your own adaptive cruise control. It'll follow the path that it was given, but it won't run into something. It'll slow down if it sees something in front of it. So it turns out that kind of reactive logic is pretty straightforward and you can put into these simulators. And what's nice now is that now, if you endow your other agents and record a data set with this logic, you now have a simulator. It will react to how you're moving. Okay. And I think an interesting way to think about how to, okay, so now I want to think about, that's just a background on what NuPlans is, or how to, more generally speaking, turn a data set into a simulator. So now we actually want to evaluate a plan. We want to do some kind of attempt at something end-to-end-ish that will control what the ego vehicle is doing. And maybe I should be a bit more clear. So we could do something end-to-end-ish, which would be a policy or a reinforcement learning algorithm that's learned that takes some perception state in and returns back acceleration and steering angle. Instead, what we're gonna, we decided to follow something a bit more classic, I think more closer to what current deployments I suspect are following, and that is a model predictive control. So here, what happens is that there's the little logic inside of the ego vehicle's head. It maintains an internal world model about how it thinks the world is going to unfold. And it does some rollouts, and then it will optimize for the best path that will get it toward its target waypoint without running into, without incurring penalties on the optimization. And so all of this is in some ways a classic control strategy. I just want to point out that even LeCun, I think, advocates for a version of this as his view of a path towards autonomous machine intelligence. Although in the document I couldn't find the term model of predictive control, from my perspective, that is what he's suggesting. But the crucial thing here, though, is that we need a really good model of how the world's going to unfold, and that very naturally plugs into all the contemporary work on world modeling. Okay, so starting point of, okay, so now hopefully we all got a sense of what this benchmark looks like. And when this was released, there was different ways of evaluating. Remember, C1 was the ego forecast, which I'm not really going to follow. C2 is actually the planner can move off the path that was in the recorded data. And C3 is the real setup where the rest of the world can react. And when this data set, or when the benchmarks was released, one sort of frustrating fact was that simple rule-based planners did much better than any learning-based solution. And this was kind of, I think, maybe one of the reasons why. Well, let's see. I still think this is a really nice data set and a really nice simulator. I'd love to hear more comments on this, but I have a feeling that because it was hard for learning-based methods to shine, it didn't get as much traction as it maybe should have. But here's a starting point that we had about how to sort of, starting with those more classical solutions, is there a way to put some learning into it where we can get better with data? And our starting observation was that if you look at these control parameters, actually, let me take a step back. You don't look at these control parameters. You look at actually the real data that was in these logs. And one of the interesting things about NuScenes is that includes different cities. What you find is some of the statistics of how people drive seem to be different. So we can measure, for example, what the typical min gap is for a driver to the next one in front. And we find that in Boston, for example, there tends to be more tailgaters. There's a peak of drivers that will follow closely, that will follow 6 feet behind the lead vehicle as opposed to 10 feet behind the lead vehicle. And so what that got us thinking is maybe if we're going to take a model predictive control approach and we actually have a little world model of how we think the world's going to unfold, maybe the world model should depend on where we're at. Because if we're in Boston, we believe that everyone else is going to drive aggressively. So that's what we should be thinking when we try to optimize for our path. And another extreme form of this, of the running joke that we always tell, is that if you ever drive in Pittsburgh, there's a specific maneuver in Pittsburgh called the Pittsburgh left, which is when if you're taking an unprotected left turn and the light turns green, it's customary that you let the other person that's making a left go first. So this is not an official rule of the road, and if you're not used to it, you will be in for a rude awakening. But it's kind of emphasizing the fact that there's actually culturally dependent factors on how people drive and the behaviors they engage in. So our starting point was that why don't we then try to uh, kind of model these behaviors with essentially inverse optimal control. All of that sounds fancy. All we really did was, uh, given that we know we're going to model all the other agents in Boston with some intelligent driver model, let's tune the parameters, the min gap distance, the max acceleration, min acceleration, so that when we tune the parameters of a controller and we run the controller with those parameters, it looks like the data that we see. So that's all that is. So we just do a grid search and optimize for the best parameters for every city. And what that tells us is that is not without surprise that when you're in Boston, if you really want to simulate the way Boston drivers behave, you should use a smaller theta 3 in your IDM controller. Um, and now you can think about optimizing this for every city. What is the best betas to use? You can even do this per log or even per agent for each individual agent that you see. Does this happen to be an aggressive driver that likes to tailgate or someone that doesn't have a max acceleration that's very high? So we go through this process of fitting these models, and then we can actually, once we fit these control parameters, then we could just roll out and say, okay, what do the agents look like when we run it with their control parameters? And this is also not surprising that if you fit a control parameter that says you're willing to tailgate, when you roll out potential features, you'll see tailgating. So that suggests that we can almost get a label for these different control parameters and all this data set, but how do we actually use it on test data when we're actually going to go and run a real planner live on robot or in the simulator? And the sort of the insight that we wanted to kind of advocate was we can reuse all the machinery people already use for forecasting trajectories, but instead of forecasting trajectories, what we're actually predicting are these control parameters. So we're trying to predict for every agent, is this an aggressive guy? And the way we're trying to predict that is we're looking at the past history of how people have been driving in the most recent 5 seconds. It's the same history one of these models would use to predict future trajectories. And then once we have these parameters that are predicted, we simply use that in the rollout for model predictive control. So at the end of the day, the final stack looks really classic. It's doing an optimization. It just so happens that the world model has a little bit of learning in it. We just try to learn, does this look like an aggressive driver or a passive driver? And it turns out that's relatively simple to learn by looking at a past recent history of how people are driving. We could do some fun visualizations of these parameters and TSNE plots and group the fits of individual agents by city. We realize, oh yeah, people in Boston do tend to tailgate, but sometimes there's tailgaters in other cities as well. I'll skip this for the moment and let's sort of get to the final numbers. So now, like, once again, we're just repurposing trajectory prediction models for IDM controlled prediction. And once you do that, we just put it into an MPC controller and you get an improvement, which is we can choose to learn IDM parameters that are specific to each city, or we can even choose to learn ones that are going to be predicted differently for every log. So even if we're in Boston, maybe at a particular sequence, it looks like everyone is being passive as opposed to being aggressive. And what we see is an improvement. And so this is maybe not, at first blush, it looks like it's not that big of an improvement, but just to point out that the max performance here is 100%. So we're actually decreasing the error by a noticeable amount. And what's kind of fun is in this world, you can play these games of what happens if you perfectly knew the control parameters to use for each other agent, if you knew if they were going to be aggressive in the future or passive. And you can show that the predicted control parameters are pretty close to the optimal ones you could fit post hoc. And what's kind of fun is the city oracle is actually not an oracle. It's a completely implementable algorithm. It's akin to saying that when you drive in Boston, you know that you're in Boston and people in Boston tailgate. So you will use that model. It seems totally fair to use a city-specific model if you're so inclined. Okay, so here's some sort of visuals. On the right-hand side is if you do a normal model predictive control with a standard fixed IDM control parameters, and you'll see a collision in frame 21 where the ego vehicle will collide with someone. Down here, you'll see collisions in frame 10 and 23 if you just use a fixed default IDM control parameters. And in our case, of course, we're going to learn how to predict the parameters based upon the city that we're in or based upon the current history of the other agents, and that gives you a little edge. Um, I'll skip this for the moment. Um, yeah, so I guess so one sort of take-home message from here is really um, thinking about, instead of putting a lot of machinery into um, predicting exactly how the world's going to unfold in terms of space-time trajectories, this is saying, well, we believe the world's going to be reactive or agents are going to be reactive. So what we're really trying to do is predict, in some sense, their rewards or their inverse control parameters. Um, and so I think this is one way of actually letting learning shine. And hopefully you can do better at this the more data that you have about learning the behaviors of other agents in your in your world that you're going to enroll. Okay. All right, I'm gonna keep an eye on the time here. That look longer than I would like. So I wanted to have two more sections of the talk. The second section is so I think if we kind of zoom back out, in the world of building simulators for helping to address the self-driving problem, I think that while there's enormous work on building better sensor simulators, I think we'll sort of need to address this problem of how do we build better behavioral models. And what this is really about is understanding motion. So there's another sort of track of work we've been involved in that really leans into the problem of how do we understand how things are moving across time from logs. And sometimes this is called the scene flow problem, in particular applied to LiDAR data. And I just want to talk about a few bits of work that we have in this direction that I think have some interesting consequences. Um, Okay. So the starting point for the work I'm going to show is an old paper, not from us, but from another group at CMU called Neural Scene Flow Prior, that talks about a method of, if you have two LiDAR frames, how you can automatically compute a flow vector that tells you how everything is moving. So if we zoom back out, if we can do all this kind of motion extraction at scale, then my claim is we can build better behavior predictors. So right now I'm going to zoom back into this problem of how can we at scale learn really exquisite models of how things are moving and changing over time in these log sequences. And so what Neural Seed Flow Plier does, it does a really kind of classic approach at this point. It learns a scene-specific MLP that if you give it an XYZ spatial location, it spits out a flow vector. And the way that it learns is with a chamfer loss. So given all the blue points, we push them through an MLP that will say how they all shift. And then we look at the chamfer distance between all the shifted points and the actual points we see in the next frame. Those are the orange. We get an error signal, and now we can optimize and learn a better MLP. And this is it's almost akin to per frame optimization of a neural rendering model. Okay. So the kind of series of work we have in this direction that kind of builds us up to something that we can learn at scale, learn something we can learn motion models from at scale, and also with hopefully high accuracy. As a first observation is that this, just like Laura was suggesting, per frame optimization, although it tends to produce good fits, it's really slow and expensive. But a simple kind of almost trivial observation is that, well, you can do all this at train time. Think about then this is a way of producing scene flow labels and just train a super fast feed forward student model that, just given a pair of frames, push it through a network and it will spit out a UVW flow for every point. And it turns out you can do this and get pretty good performance, basically a model that's just as fast as the fastest feed forward models, but it's as performant as these per optimization models. And you can do this without ever needing any human labels, because you can just use this very expensive per scene optimizer as the teacher. So we had a couple other interesting, for me anyways, I thought this was interesting, works in this direction, which is if we think about ways of building models that can really understand motions in a self-supervised fashion, could we actually use pseudo-labels, predictions from an explicit supervised model to self-train on? So the starting point for this is, if you look at existing methods for scene flow, what we find is that actually small objects disappear. They're not modeled very well. And this is very concerning if you think about people. They're not modeled at all in any of these motion data sets for scene flow. So we came up with a kind of almost ridiculous strategy, which is, well, one way of predicting the motion of every point is let's just run an explicit detector and tracker, and that will predict the movements of all these bounding boxes, and let's just project that to the points and see how well does that do with scene flow. How well does that do? How well does that do with the scene flow problem? There's this comically titled paper, I can't believe it's not scene flow, that basically outperformed all other methods for scene flow just by solving the supervised problem, just downloading a detector and tracker and estimating how things move. And this really shined for small objects because otherwise they just get swamped when you try to do this self-supervision. Um, Okay. So that was sort of an interesting eye-opening thing that to me it was interesting because it kind of, even though motion estimation is a low-level problem, this to me kind of challenges the notion of what is high-level perception versus low-level perception. I like this because a true benchmark should just define a task, and maybe we'll discover that high-level cues are better for addressing that task. So maybe the best way to estimate motion is to first explicitly detect and track things, which is what this plot suggests. But there's a recent piece of work that the collaborators Kyle Vetter did, which was a really nice extension that almost went back on this. It went back to the test time optimization, so this is really slow, but it's a really seemingly elegant way to think about long range motion estimation from LiDAR. And let me just sort of dig into it. This is much more like the first neural scene flow prior work that I showed. And the insight that Kyle had was just train a neural scene flow model, or like a deformation nerf, if you will, but instead of training it on a single pair of frames, train it on a long sequence. And so you're training one model that takes as input an XYZ and now a timestamp, and now it will spit out the flow at that space-time location. So at some level, it's a really simple architectural change, but conceptually what's happening is that you're essentially sharing structure between all these per frame models across an entire sequence. And that by itself, just doing that, um, uh, allows you to learn much more accurate long range flow models. And we use the term Eulerian flow as opposed to Lagrangian for two reasons. One is I think this is actually different than the typical way we see motion being modeled for neural reconstruction with nerfs or splats. Usually what happens is you have some canonical frame that represents the structure of the world, and then you learn a deformation model from that canonical frame. And so what you can think about that, like there's this old kind of from the simulation literature, this notion of two different approaches to talking about motion. One is Lagrangian, where it's more particle based. So you actually have a particle in some canonical state, and you track how it moves. There's another way to characterize motion of a fluid, where you just characterize for every point in space how much fluid is moving at that position. So my claim is what we're actually training when we train this deformation field is it's an Eulerian model. You can query it with any point in space, and it returns back the flow, the fluid flow at that space, at that point. And the reason why I call it Eulerian is that you can actually chain a bunch of these things together to get a long range estimate of flow, which is what those visualizations were. Here, it's essentially doing Euler integration of all these little difference vectors. But this ends up producing a pretty dramatic improvement in the ability to track points over a long time frame. So once again, this was surprising to me because this is essentially not the big data story. This is the per scene optimization story. So the downside of this is painfully slow. So what Kyle's trying to do now is to do the same story of distilling this into a feed forward model that can be run efficiently on vehicle or on car. All right, so I have 5 minutes left, and maybe I'll just briefly advertise something that I think another speaker will talk about next, Nihar. And that is in this goal of trying to produce accurate simulators where the thing we really want to see is interesting behaviors. There's this sense of we kind of in order to populate our simulators with interesting and compelling scenarios to really stress test our stacks, we'll have to kind of search for needles in a haystack. The hypothesis that we're making is the first thing we want to do is, given the loads of terabytes of data that we have, we want to find interesting and safety critical scenarios from which to identify behaviors and then populate simulators with those kinds of behaviors. And so this is motivated by I remember one time when I wore my Argo hat in industry. I remember one current refrain was that in some sense it's not enough to build a stack that works. You have to build a stack that is demonstrably that is can be demonstrated to work. What that means is you have to make a safety case. You have to assemble a really stressful validation set that spans all these different operating domains, weather conditions, scenarios where pedestrians are walking in an occluded fashion behind another car. Um, our thinking was that this seems to be a really nice place where we can lean into this incredible effort and innovation on vision and language and multimodal processing. So, imagine if you have terabytes and terabytes of data, and you want to find a particular sequence of a vehicle making a left turn through an ego vehicle's path while it is raining. Um, the claim is by assembling large language models and even programmatic instantiations, we can almost build code that can then take off-the-shelf detections and tracks and try to surface these interesting scenarios. So one of the things that Nihar and Kanan did, I'll just give another example of these sort of interesting prompts. An ego vehicle behind another vehicle being crossed by a jaywalking pedestrian. These are all prompts that are motivated from a planning centric perspective in the sense that we want to be able to validate and train a planner on this kind of data. So the first thing we want to do is find these needles in a haystack in large data sets. Um, I'll skip the method in which we kind of put this together, but the take home message is that we tried to formalize this as a scenario mining challenge that Nihar will talk about in a bit, where it's a bit like an integration of maybe it's almost like an advertisement or an invitation to the huge kind of growing body of work on vision language modeling to think about the problems of data curation for an AV world, where we query with particular interesting scenarios and we link that to actual code that can surface and retrieve interesting behaviors that we can then use to populate and validate our simulators. I won't go through the ways of measuring accuracy. But maybe I'll then kind of bring it back to the sort of summary. So building off of what Laura was saying, it seems like simulators are going to be an important part of the stack for both training and validating planners. I thought NuPlans was a really, to me, really nice attempt at trying to formalize the problem of how do you take a recorded data set and turn it into a simulator. And I think there's interesting ways about trying to merge classic autonomy pipelines with data-driven world modeling. The second part of the talk really focused on this. If we really want to model behaviors, getting massively large data sets of how things are moving is really asking about solving some form of the scene flow problem. And I think there's been some sort of fun innovations in that space. And then lastly, to kind of find interesting behaviors and scenarios, I think we can kind of make an appeal to all of the interesting work on vision language modeling. And I guess I will leave it there. Thanks.